So today we're going to talk about a subject called mean value theorem. I almost have to read my notes here because I can't believe what I'm going to say. We're actually there's a predecessor to this we're going to look at too called Rolle's theorem. There's an irony involved with these theorems. They are both critical to the subject of mathematical analysis, the area of math that examines the underpinnings of calculus. I was kind of elated to learn a couple days ago, we have 3 math majors in my class. I love that. You math majors, you want to pay attention really close. This is going to be a big deal in a year or so. But the irony is that neither of these theorems will be useful to most of the rest of you. They're in the curriculum. I need to cover them. I'm not going to emphasize them on exams. There are a few interesting examples where you can do something with them. It's neat, and we'll look at that. But overall, their main purpose in mathematics is when you're doing analysis, when you're doing proofs, and it's just kind of like a little pop-up. You know, you're doing some proof somewhere, and you're trying to get from A to B, and then right in the middle somewhere, you have to go, oh, the mean value theorem. So it's very important, but again, you're not going to find it important if you're a physicist or computer scientist. At the same time, they're kind of intuitively obvious, so at least we can look at them and see what they say and kind of figure out, you know, how to use them. So first theorem I'm going to go over is Rolle's theorem. Put the apostrophe in the right place. No doubt, Mr. Rolle, Ms. Rolle, is a mathematician. I'm really not familiar with. I've never heard anything interesting about them. But be that as it may, here it goes. First, we have a function f, which is continuous on a closed interval a comma b. Number 2, we have that f is differentiable on at least the open interval a comma b. And we have that f of a is equal to f of b. So that's the premise. That's what we have to start with. So as an example of what this might look like, we might have some function. Doesn't have to be a parabola. It's got a point A and B, and f of A equals f of B. It's continuous and it's differentiable. So what our theorem says is there exists a C on AB such that the derivative at C is 0. So what that says is there's some point here C, this is A, this is B, there's some point C where the tangent here is horizontal. The derivative is 0. That's Rolle's theorem. It kind of looks obvious. I mean, you have 2 points on the graph. The function has to come back to them. It's continuous, it doesn't have any breaks, and it's smooth. It doesn't have a sharp point like an absolute value would have. And therefore, at some point, it the derivative has to go to 0. Now, Rolle's theorem doesn't say there's only one c. So you could have a situation like this, where this is A, this is B, and now you kind of have C1 and C2, where the derivative is 0. There's no limit. Okay. I guess in the extreme case, if f is some constant, you can have point A and B, and every point in between is a potential C, has a derivative of 0. All right, so it'd be nice to know, have some idea how, why this is mathematically true. So we're going to just kind of go through a very loose version of the proof. So we take some function. I can draw it the same. Doesn't really matter. I don't want to draw something that misstates the conditions, but this will do. We look for some point between A and B, and if its derivative is 0, we're done. We found that point. If, on the other hand, the derivative is positive at our point, well, we know A and B, f of A and B are equal, so if it's increasing at some point, it has to decrease at some point. What goes up must come down. And since the derivative is continuous, by the intermediate value theorem, just review that real quickly. You have some function goes through points A and B, it's continuous. Well, it has to pass through each value between them. So if it has to pass through a positive value and get to a negative value, then it has to pass through 0 at some point. So by the intermediate value theorem, there exists a C like that. Now, I said, well, you picked a point that's increasing. What if it's decreasing? Well, then the opposite argument holds. If it's decreasing, it has to increase to get back to, from f of A to f of B. There's some nice consequences to this, logically. So if I take something and I throw it up, whoop, Catch it? Well, we know as it goes up, it slows down, stops, it comes down, back down. So Rolle's theorem, since, back at the same place eventually, Rolle's theorem tells us that at some point in its trajectory, it's motionless. Its velocity is zero. That is, at the top of its arc, it's zero. You can kind of write that in some manner. If x is, I don't know, negative at squared, right, is a gravitational constant. I guess I'm going to start throwing it up with some velocity. This tells me at some point the velocity, derivative of x, is going to be zero. That is, some x1 and x2, it's, I don't want to write it this way. If its position is f of x, its derivative at some time has to equal zero. So that's Rolle's theorem. He said there's some things we can do with it. They're a little obscure, but kind of neat from a math point of view. Here's an example. We have the function f of x equals x cubed plus x minus 1. And we want to prove it has exactly one root. No more, no less. So, how do we go about that? Well, we can look at the certain values of f. F of 1 is 1, and f of negative 1 is negative 1 plus 1 minus 1 minus 1. This is a continuous function because it's a polynomial. So our intermediate value theorem tells us it has to pass through all the values between 1 and negative 1. So, for some c, it's going to equal 0. So that's, point 1 is it has a root, has one root. Point 2 is it has only one root. How are we going to show that? That's where Rolle's theorem is going to come in. So this is going to be a proof by contradiction. We're going to, I should say something about a proof by contradiction. Proof by contradiction, if you're trying to prove something, you assume the opposite. And then you show as a consequence of the opposite, you get a contradiction. So our assumption here is that there's some f of a equal f of b equals 0. In other words, two roots. We're going to assume that and see if we can find a contradiction. Well, by Rolle's theorem, since we have f of a equals f of b equals some value, there has to be some c such that the derivative is 0. Does that make sense?
This is just, Rolle's theorem tells us, if this is true, we have to have, at some point, the derivative 0. So let's take a look. F of x is x cubed plus x minus 1. Well, we know its derivative is power rule 3x squared plus 1. So by Rolle's theorem, this has to equal, there has to be some value here equals 0, so let's see if we can find it. Oh, well, wait a minute. 3x squared is always greater than or equal to 0, so 3x squared plus 1 is always greater than 0. That's our contradiction. So that's our proof that it has only one root, which is what we're trying to prove exactly. So that's an example where Rolle's theorem lets you prove something a little, a little obscure, but useful.
Professor,
Yes,
will we have to do proofs on our final or on the next one?
I'm not going to ask you to do proofs on the final or the midterm. You will have a homework problem where you're asked to attempt to, get up this hill. Yes, it'll be fun, maybe. Yes.
So because 3x squared plus 1 is always going to be bigger than 0, that means it has one root? And only one root?
Okay, yeah. Follow the logic. This is what we're trying to prove, that it has only one root. We've shown it has one. We assume what we're trying to prove is wrong. We assume it has two roots. If it has two roots, this is the case. That's what a root is. F of a equals 0 is a root. So by Rolle's theorem, there has to be some value between a and b where the derivative is 0. Well, we look for that. We look for the derivative to be equal to 0. We find it can't be. That's our contradiction. I'm trying to think of a way to describe that in more physical terms. So, we collect marbles, and we want to prove that marbles come in different colors. So, proof by contradiction, we say, let's assume all marbles are red. Okay? And we go out, we go to the store, and we buy some marbles, and there's a blue one and a green one. That's a contradiction. So that proves that marbles come in multiple colors. It's not a good example, because the direct proof is even better. Let's go find two different color marbles. That's the logic of a proof by contradiction. You assume the opposite of what you're trying to prove, and then you show that leads to a contradiction.
So if it could equal 0, then we would know it didn't have more than just one root.
Oh, yeah. We're assuming it has, really what we're assuming here is it has at least two roots. Yes. If it has two roots, a and b, they're f of a and f of b is 0. And that leads us to, well, wait a minute, where is the derivative 0? It can't be. going to start the break early, and then we'll go on to the mean value theorem. So, want to take a hour or a walk or a text break. Oh, sorry. Oh, I know. I'll get it. Sorry.
You have to get into the total.
How did I miss it?
Yeah, I think you got that one.
It wasn't bad. I just ran out of time. I finished I got half done in the last problem. I spent the multiple choice pretty quick. It was like a half hour. I just classic multiple choice, and a lot of it's they're local this output, and I just copied it and ran it. But that's when we have hours, and then you have a choice on they give you a logic options for problems. One of them was worded I wanted to pass an internal as a parameter, and I was like, oh, talking, and I spent too long just kind of looking at it and being like, what are you asking for? Yeah, one was 20 points, and then the other one was 30 points. So the 20 points you choose between there's a chronographic problem, which was super easy, but you wanted it in a function, and you wanted, I don't know what you got for the parameter, I think I called the turtle, and the other part just it ran through. But the actual programming part is super easy. And then the next one was a password checker, or one was a
Password checker
you have to know how to check if you have all your string things. You have to use a text editor. And then when we write stuff in Python, it's
Confusing. Oh, why, thank you. So, and does anyone know the page numbers for homework 4? Oh, product and quotient. Okay. So, number 8. Differentiate e to the x over 1 minus e to the x. Number 8 on 189. X over minus e to the x. I wonder why that would be difficult. And then number 35. Number 35 is find the equation of the tangent. X squared over 1 plus x at the point have. Really? What? Yeah, that's right. There's a few of these. And also number 10. No. What's number 10? And also number 8. Differentiate g of x equals 2. X plus 2 times the square root of x times e to the x. It's funny how everyone knows the derivative of e to the x, and yet it gets confusing somehow when you start combining it either with the product rule or the chain rule. So let's take a look at these. This is a product, so we use the product rule, f prime g plus p prime f. So it's x plus 2 square root of x prime e to the x plus x plus x times the derivative of e to the x. Well, derivative of x is 1. Derivative of the square root of x is 1 over 2 square root of x, but we've got a 2, so that cancels. Is our e to the x plus x plus 2 square root of x. Derivative of e to the x is e to the x. Perfectly good answer. If you want to make it look pretty, maybe take out the e to the x. 1 plus 1 over square root of x plus x plus 2 square root of x. And you could combine this in some ways, but it wouldn't be all that important. Does anyone have a feel for why? I mean, what would go wrong here? Is it just new applying the product rule, or just again, I'm thinking that e to the x itself might be sometimes simple things, kind of make people busy. All right. Quotient rule, I know, I had to kind of re-cement the formula back in my head. You can always look it up or put it on a cheat sheet. So, the derivative of f over g is f prime g minus g prime f over g squared. So e to the x is our f. So derivative of e to the x times 1 minus e to the x minus g prime, derivative of 1 minus e to the x times e to the x all over e to the x squared, or e to the 2x. All right, e to the x, that's just, derivative is just e to the x, 1 minus e to the x. Derivative of 1 minus e to the x, well, derivative of 1 is 0. Minus derivative of e to the x, that's e to the x times e to the x. e to the 2x. Again, oh, with minus and minus, that's going to be plus. We have a factor of e to the x on the top and the bottom.
Wouldn't it be 1 minus e to the x squared on the bottom?
Oh, thank you for catching my error. Well, that's going to save me some trouble. All right, so all I could do is maybe gather terms e to the x minus e to the 2x plus e to the 2x over 1 minus e to the x squared. And so I guess these drop out. All right. It's not pretty, but, you know, it's not every problem turns out nice and pretty. Okay, I ran over my board space here, so I'm going to, well, I guess I can just draw a separator here. Okay, so this problem's more complicated. We need to find the derivative because we want to find the equation of the tangent at that point. So again, we have to use this formula. So derivative of x squared times 1 minus x, 1 plus x here, minus derivative of 1 plus x times x squared over 1 plus x squared. Why did I put a 2 there? Derivative. So we have 2x times 1 plus x minus derivative of 1 plus x, that's just 1, so minus x squared, 1 plus x squared. Now, at this point, you could simplify it, but we really don't need to. What we need is, this is f prime of x. We want f prime of 1 at this point. We want to find the slope of this curve at that point. So we can just plug in 1 here, which is kind of easy. It's just going to be 2 times 2 minus 1 over 2 squared, or 4. So it's just going to be 3/4. At that point, we're back to our algebra class. Y equals mx, well, m is 3/4 plus b, or I know some of you know the slope point form, you can just kind of write it out. I kind of like to do this. So I plug in y as a half, x is 1 equals 3/4 plus b. So b turns out to be half minus 3/4. What's that? 2/4 minus 3/4 is minus 1/4. Okay, so that, you know, that's my equation. Something like this, I mean, if you like that kind of thing, you could go to Desmos, graph this, and see it. In fact, it looks like it works. Yes?
Is the final answer for the one you just did before, or not for that one, but for the e to the x one, e to the x over 1 minus e to the x squared, is that the final answer? Because the grader marked that wrong on the homework.
Oh. Well. There are 3 possibilities here. One is I made a mistake, the same one you made. Another is I made the mistake when I wrote the grading sheet and the grader didn't pay any attention. I'll bet that's why she thinks a lot of people got this wrong. It's probably wrong on my solution sheet. My apologies. If you had nothing else wrong, hand it in. You know, we can upgrade you to you probably got a 3.
Yeah.
You know, well, hand it in, you get a 4. You could actually just, Oh my God. I just suddenly had a flashback. Time traveling 40 years ago. I had a high school teacher who said, in the privacy of your own home, you can pat yourself on the back. There's no credit difference between a 3 and a 4. So if you want to hand it in, I'll upgrade it. Yes?
I just wanted to confirm, for the one that we just did, the equation is y equals 3/4, that's not solved, right?
Unless I made a mistake, yeah.
But that's what I got in this one, so it's a
You did hear what I
yeah.
said. Yeah, it's possible. If you got a 2, maybe hand that in. We'll want to upgrade it. My apologies. Somebody could send me an email. I'll go change my solution sheet. I guess nobody's bothered for now. It would explain why a lot of people would have gotten them wrong, because they got them right and I got it wrong. And she didn't check. All right. Okay, thank you. All right, let's move on. So, before I describe the mean value theorem, I'm just going to draw a picture, because I think picture really helps. We have Rolle's theorem, which says, f of a is f of b, therefore there's a c, which that c prime, f prime of c is 0. Mean value theorem is kind of the same ideally, kind of lopsided a little. You have some function and 2 points A and B, and we're going to have the same conditions. It's going to have to be continuous and differentiable on this interval. And instead of the derivative being 0, we're going to take the slope of the line between A and B. So what's that? That's going to be f of b minus f of a over b minus a. That's m, or if you like, delta y over delta x. And the mean value theorem says that there exists a c such that the derivative at c is equal to this. That is to say, there's some point here, some c, where the tangent is going to be parallel to this line. It's going to have the same slope. So I guess I should write that out. Mean value theorem. F is continuous on the closed interval AB. F is differentiable on the open interval AB. Then there exists a C in AB such that f times C equals f of A minus f of B over A minus B. You can see that if you just set if it just so happens that f of A is equal to f of B, then you just get Rolle's theorem. Just if you take this diagram and kind of transform it, you can rotate. If you rotate the axis, you just get Rolle's theorem, which is a little simpler. All right. What might we do with this? Well, we might have an example where we want to find C. So, for example, we have f of x equal to x cubed minus x, defined on the interval 0, 2. Well, let's see. It's polynomial, so it's continuous on that interval. It's a polynomial, so it's going to be differentiable. So there should be a C, there should exist a C, such that f prime of C equals f of 2 minus f of 0 over 2 minus 0. So we just have to figure out what C is from this. So f of 2 is 8 minus 2, which is 6. F of 0 is 0. And we have 2, so we're just looking for, we know it must exist, we're looking for that particular C. Well, we need to find the derivative. Derivative of x is equal to 3x squared, and we want it equal to 3. So we, of course, have x squared equals 1, or x is equal to plus or minus 1. Just like Rolle's theorem, the theorem doesn't say there's only one such C. It says there's at least one such C. Oh, but wait a minute. We were interested in this, in just this interval, 0 to 2. So that kind of, it's just the positive one. The negative one is on that interval. I think I did something wrong.
Where did you get the 6?
I plugged 2 into here.
Oh, okay.
8 minus 2 is 6. Yeah, according to my instructions, I made a mistake.
It's 3x squared minus 1 on the f prime of x. It's 3x squared minus 1 on the bottom.
Ah, thank you. Have to fix that. Like that, right?
Yeah.
All right, let's try again. F prime of C equals what? I plug in, wait a minute. I plug in C, I'm sorry. You're completely correct, and I've completely spun myself around. What am I trying to do here? We're trying to find this equal to 3, is that right? Yeah, okay. 3x squared equals 4, x squared equals 4/3, or x equals square root of 4/3. And again, it's plus or minus. We should write that as 2 over square root of 3. It's plus or minus, but the minus wouldn't be in the interval. I don't know why I should bring in my Tom Lehrer recordings where the mathematician sang funny songs and where he gets the wrong answer. It's not what's important, it's knowing how to do it. All right. Okay, well, that's most of what we can do with this wonderful theorem in this class. But just to give you a flavor of what we might do in the analysis class. Nothing over anybody's head here. I want to prove that if f prime of x is equal to 0 on some interval a, b, and f is constant on a, b. It kind of sounds kind of obvious. I mean, if everywhere you look on here, the derivative, the tangent to the function is horizontal, and it means you can't go up and down, right? So it should be a constant. But how would you prove that? Well, we would pick two arbitrary numbers, x1 and x2. That are between a and b. Any two numbers. We have some function, take believe it's not constant. We just pick two numbers, x1 and x2. So by the mean value theorem, there's some c such that f of x2 minus f of x1 over x2 minus x1 if there's some c where this is true. But we just said this is 0, right? Probably should have said x1 and x2 are not the same. So I can multiply this out and I get f of x2 minus f of x1 equals 0, or f of x2 equals f of x1. That is to say, any two numbers I pick between a and b, because of the mean value theorem, and given that the derivative is always 0, these two have to be equal. So we've proven what we wanted to, that f of x is constant on that interval. That's what you can do with the mean value theorem. There'll be some homework, just a few homeworks on this issue. There probably won't be anything on an exam because we're not taking analysis. All right, any questions on this or any other homework problems you might help you with? I know it's a little early, but I'm gonna head down to my office. People need to see me there. If you're taking the exam, come down and we'll get